Okay, so what I want to do is talk a little bit about how do we, how do power plants work, essentially? How do steam power plants work? And while a lot of the discussion on power plants, and that's most of our power in this country, comes from the steam turbine power, steam turbine generator, okay? And most of the discussion on generation of power comes from, well, where do we get the heat from, basically? Do we get the heat from coal? And people don't like coal because it has a perception of being kind of dirty, right? Bad for the environment. Or natural gas. People don't like natural gas, but they like it better than coal, right? It seems to be a little cleaner than coal. Or nuclear, which is very clean, but people don't like nuclear either because it seems dangerous, right? So, yeah, so we've got all those three. And maybe somebody could rationally argue that it is dangerous given events. Of course, you could. So, so you've got those three things, the source of heat, coal. You've got natural gas, nuclear. You could have some oil. There's a little bit of oil out there as well. But that is a big chunk of our power in this country, 85% maybe, okay? The only other ways we can generate power is wind and solar and some hydroelectric, all right? That's pretty much it, okay? So this is very important to keeping the lights on, right? This process is very important to keeping the lights on and having power. And all those things, whether it's coal, natural gas, nuclear, uses this basic cycle, okay? So let's go over the Rankine cycle, all right? So where do we begin? Well, I'm going to begin, okay, here, and we're going to have water. This is liquid water that's going to go into a pump, okay? So we've got a pump here. Okay, we're going to call this state 1. And it's basically going to be liquid water that's going to go into a pump. Okay? And the pump, the purpose of the pump is to increase the pressure of that water, liquid water. Okay? And so it's going to increase that pressure. It's going to take it to a much higher pressure than where it's at before. Okay? Then what we're going to do is we're going to come out of that pump and we are going to go into a boiler. What comes out of that pump, by the way, we're going to call it state 2. Okay? And then we're going to take it into a boiler. This is where you have either the coal, natural gas, nuclear, oil, whatever. You have a heat source, right? Okay? You have a heat source. We're going to take high pressure liquid water. We're going to bring it into our boiler, and we're going to have obviously some kind of Q in here, right? All right? We're going to have Q in. We're going to bring in heat. We got to burn something. That's going to take that liquid water, and everybody's seen how to boil water, right? You know that. And we're basically going to boil it, right? We're going to boil it. We're going to, in thermodynamic terms, we're going to take it from compressed liquid water, and we're going to take it into most likely superheated water, okay? Most likely superheated. I guess it could be just saturated vapor. It's possible that it's not superheated, that it's just saturated vapor. But we probably want it to be superheated. We probably want that would be better. Okay, so we got superheated water coming out, steam coming out of the boiler. It's at a high pressure, high temperature. Okay, and that's the best for taking it into a turbine. So then we take this very high temperature, high pressure steam, and then we blow it through the turbine. So basically, you can kind of think of it as a turbine as a blade. There's some blades, okay, and we take this high pressure, high temperature steam, and it just goes through the blades and spins those blades, okay? Spins them, and that spinning creates energy, like a generator. Okay, so this is a turbine. Okay, and this is state 3 going into the turbine. And then what comes out of the turbine, we're going to call it state 4. Typically, what comes out of the turbine is going to be probably somewhere near saturated vapor, maybe with some liquid in it, like a saturated liquid vapor mix, but probably not a lot of liquid, because if you have a lot of liquid in your turbine, it can damage the blades. It's not very good for it. So it's probably pretty close to saturated vapor. or somewhat saturated liquid vapor mix at state 4. All right. Then what we're going to do is we're going to run it through a condenser. Okay? We run it through a condenser. What does a condenser do? Well, it condenses. Okay? And a condenser takes the steam, okay, and turns it back into liquid. And obviously, when you take steam, some hot steam, and you turn it back into liquid, you're going to lose some heat. You're going to have some Q out. Okay? You're going to lose heat. Okay? And then this liquid, which comes out of the condenser, goes back into the pump. That's pretty much the Rankine cycle. All right? We don't like to lose heat, but you kind of have to do it because, first of all, the second law of thermodynamics says you have to have some heat loss. Okay? The second law says I can't take all that heat in and turn it into work. Okay? And by the way, of course, I get work out of my turbine. That's the whole point, right? The whole point is that is the whole point of this process is what happens with the turbine. The turbine gives me work out. Essentially, it turns, right? I hook it up to generator, right? I generate electricity. Then I hand this off to the electrical engineers. They say, oh, here's my electricity. You guys and gals figure out how to take it and get it to everybody's houses and businesses and all that. Okay, but yeah. But my job's done. I generated electricity. Here you go, electrical engineer. Okay, so that's the workout. Okay. Oh, and by the way, I do have to pay a price for all this in terms of work. Part of that electricity that I generate gets to go to the pump. Yeah, I have to plug the pump in, so I do have some work in as well. Okay, so yeah. Yeah, it better be. It better be. Yeah, exactly. This thing, by a huge factor. Yeah, it better be way bigger out than in, or you have a really bad power plant.
Or really problematic pump.
Yeah, a really problematic pump. Yeah, exactly. Yeah. And that's partly why we have a condenser in the first place. Because as I've talked to you before, there's a whole lot less energy in pumping up water to a higher pressure than it is vapor or gas. Okay? And the amount of work that your pump has is very minuscule compared to the amount of work generated, hopefully, in theory. Okay? So, because you're pumping up water, and that's the key. You're pumping up the water, liquid water. Okay? Now, we always like to make some assumptions, some simplifying assumptions in this process, okay? And the Rankine cycle does that. We like to make things easier for you, okay? So this is good. So each device has an assumption attached to it. For instance, we assume the pump is isentropic. Okay? All right, so, okay, you told me it's an isentropic pump. And when I say the word isentropic, I hope the first thing that pops in your mind is constant entropy. Okay, yeah, constant entropy, which if I look at this diagram you've drawn me, isn't that suggesting S1 equals S2? And that would be correct. That's what we'd be saying, S1 equals S2. But we have an isentropic pump equation, okay, and this makes it even easier. And that says that the work that we have to put into the pump, okay, we don't like to do this, but we have to, the work input of an isentropic pump is equal to the specific volume of whatever we're pumping multiplied by the pressure that we're pumping it to minus the pressure that we received it. Okay, the pressure difference. Okay? So that equation there is what we're pretty much always going to use for pumps. Okay, I'll tell you. Unless I give you a pump isentropic efficiency, which I guess I could, but this is basically, if it's purely a pure isentropic pump, you use that equation straight up like that. Okay? So that's easy. And by the way, the reason that equation is so good for us is because when water is in its liquid form, this V is very small. It's very, very small. This number here is like 0.001, right?
Yeah.
Yeah. So when water is in liquid, this V is very small. Specific volume is very small. Therefore, the work input is very small. That's good because we don't want to have a lot of work in. We want to have we want to have mainly work out. Okay. Second thing, the boiler. We assume it's a constant pressure boiler. Okay, got that? So in this case, practically what that's saying is P2 equals P3 if you look at the numbering that I have, right? We're assuming that as the liquid comes in and we boil it, that it pretty much occurs at a constant pressure. Is that totally true? No, but it's pretty close. It's reasonable.
Wow.
So
Why not? Because
so-
if it's like just an open container with, the pipeline straight in, pipeline straight out, shouldn't it?
Yeah. In theory, sure. Yeah, exactly. But you can have a little bit of pressure build inside a boiler. It can happen. So it depends on how the process is done. So, but it's not.
I'm guessing small.
So yeah, and you could have pressure loss in the piping. That's another thing. That actually is probably more common. Is that you have a loss of pressure in the piping. So
Do with dynamics.
yeah, it has to do with this piping that you learn in fluids, that if you pipe something long enough, you're going to lose some pressure as you pipe it. Yeah. Oh, yeah. So it has to do with the, like the roughness of the pipes and things like that. And so, yeah, you'll lose a little bit there. That's really more what it is. But these are minor. Okay. So that's another thing. We also assume we have an isentropic turbine. Okay, so that means that S3 equals S4, okay, the turbine, isentropic. All right, now, real turbines probably aren't going to be exactly isentropic, but they can get pretty close. They can get isentropic efficiencies of 95%, so this isn't too bad. Yeah. And then lastly, the condenser. We assume that occurs at a constant pressure as well. So practically speaking, that says P4 equals P1.
So couldn't our process be like on a graph? Couldn't we like put the axis on it?
I'm gonna graph it. I'm just about ready to do that. Yes, I'm about to do that. Yes, I'm just about ready to graph this process. Yes, but I'm going to do it a little differently.
Picture like the pump and the turbine are isentropic, and the boiler and the condenser are
Constant pressure. Yeah.
and they're across from each other.
Yes, yeah. I guess the best, if you think that way, the cleanest would be to draw a pressure versus entropy graph, a PS diagram. Unfortunately, nobody in thermodynamics ever draws a PS. They do draw a TS, and that's a very common diagram. So that's what I'm going to draw for you. We are going to draw a TS, temperature versus entropy, TS, okay? And I'm going to diagram this thing for you. You got to draw the dome. A dome, something like that, okay, on the TS diagram. So here's what we're going to do. Let's draw this up. This thing starts out, they all look about the same, yeah. Technically, you want to get into it, and they look a little differently, but practically speaking, we always draw them pretty much the same. Okay, so very, very close. Okay, so there's your TS diagram. Recall what's on the left is compressed liquid, what's in the middle is the saturated liquid vapor mix, right? And what's on the right is the superheated, okay? What you're starting with here at state number 1 is saturated liquid, right? That's before you pump it. So before you even pump it, it's saturated liquid, okay? That's what comes out of the condenser. The next thing you do is you pump it. Now, if you're going to have sat liquid and you're going to pressurize it, you're going to increase its pressure, well, then it has to be compressed vapor. That's the only way to compress liquid. Compressed liquid has to be compressed liquid. That's the only thing you can do. So it's going to look like this. Constant entropy, it's going to go up here. It's going to increase temperature. and it's going to have constant entropy up to about there. It's going to be a very small little line there, a vertical line that that just goes slightly up. It will increase the temperature. When you pump water, you'll increase its temperature a little bit. Not a lot, a little bit. Okay. Okay, so now we boil. From 2 to 3 we boil. This is what it's going to look like. First, you're starting out as basically compressed liquid. So you're going to boil at a constant pressure. You're going to get to the saturated region, and then you're going to go across, and then you're going to kind of go up a little curve like that. Okay, something like that. Okay, and we're going to get to this state 3. I'm assuming that what leaves the boiler is superheated. That's why I drew it that way. It doesn't have to be. I suppose it could be saturated vapor, but I'm going to assume it's superheated because that's mostly what it is. Okay? The next stage is from 3 to 4 goes through your turbine. This is going to be constant entropy, so it has to look like this, and it's then going to hit somewhere down there. Okay? Call that 4. Okay. And then last but not least, these two have to sort of go straight across, so, you know, if yours is a little, but it's going to basically go like that, straight across. Okay? Pretty much has to go straight across, like that. Because it's a constant pressure from 4 to 1, and if you have a constant pressure and you're inside the dome, you have a constant temperature as well. So 1 to 2 has to be a vertical line. 3 and 4 have to be a vertical line. 1 to 4 pretty much has to be a horizontal line. And then 2 to 3, that's kind of that's a weird one, because it's kind of a bunch of stuff there. Okay? That's a TS diagram. We haven't done a lot of those. But this kind of shows you the cycle, the Rankine cycle, graphically. Now, why do I bring this up? One of the reasons I bring this up is I want you to kind of shade this area and visualize this with me. That green shaded area is essentially the network of the cycle. The network of the cycle. What that means practically is that I want the most work possible out of my Rankine cycle, right? I basically want the shaded area to be as big as possible. Okay? I want this area to be big. Okay? So what that says is that I probably ought to think about how I could raise the top of it, right? How can I make it bigger by raising it up, the top? Well, that means basically run it at a higher pressure, okay, which I'll talk about in a moment. Also, that line, the vertical line from 3 to 4, if I want this region to be bigger, maybe I can move it to the right more, okay? Well, there's some things I can do there as well, okay? So this is the very basic form. But then what engineers did as we started to figure out how to make these cycles better, a little more efficient, we figured out some techniques, some things we do that are going to improve the process. So this is the standard. But now let's talk about improving it, okay? How can we increase the efficiency of steam power generation, okay? How can we do better? Because this is good, but, you know, let's say your boss is saying, look, we're going to build this power plant. We got to get everything we can. This is going to be a $50 million build. I want every inch of efficiency I can get here, okay? How can we do this? Because even a slight difference in efficiency can save millions of dollars down the line, okay? So how can we increase the efficiency? Here's what we can do. And this is pretty much what all modern power plants do, each one of these 3 things, okay? The first thing we can do is something called reheat, okay? And reheat looks something like this. Let me draw you a little diagram. Let's say we got a boiler, okay, like that. And let's say we bring in water to the boiler and we heat it up. Now it's going to be super hot. It's steam, right? And then we take it into a turbine, like that, okay? Now, if we were before, we would be done. We would say, okay, I built my turbine and I'm done, right? But what if you did this? What if you said, you know what? What if I took it off this turbine, brought it back into the boiler, heated it up some more, brought it back out, and then brought it into another turbine? Could I do that? Yes. I can do this. And then instead of having one turbine, I have two turbines. And we typically call the first turbine the high pressure turbine. Let's call it high P. And then the second turbine, we'll call it the low pressure turbine. Okay? It turns out if you use this reheat, okay, you can actually increase your efficiency by having two turbines instead of one. And you reheat some of the steam. You heat it up a little more, and then you bring it into another turbine. And you do two instead of one. Now, the question you might ask, is 3 better than 2? Yes, it is. And then is 4 better than 3?
Yes.
Yes. Is 5 better than 4? Yes, yes. So when do we stop? How do we stop? Well, why do we have 57 turbines? You know? Yeah, I mean, basically, it's a law of diminishing returns. You've ever heard that one before?
So it's not a straight line.
So it's no. And so what happens is that every one of these you add, you get a little more out of. But at some point, economics comes in, and you say, look, it's going to cost us an additional $2 million to put another turbine in here, and you're only going to get so much efficiency that it's going to take 6 or 7 years to pay it back, that $2 million? We don't do payback. The industry doesn't do payback periods of 6 or 7 years. That's not worth it. Okay? You just too many unknowns for that. So at some point you stop and go, this is enough turbines. Okay? Is it 2? Is it 3? Is it 4? Yeah, but it's not a lot. Okay? It's not many more than that. Okay? I'm sure you could find some power plant out there that has 7 or something, but I've never heard of it. There are some, but at some point the economics come in. It's just not practical to keep building more and more turbines in the cycle. But very common that we say, okay, use reheat, multiple turbines, you're going to get more efficiency. Now let me show you what this means practically. Okay, I'm going to go down here and I'm going to show you that same TS diagram. Okay, same thing. So it's going to look the exact same. This is just a repeat of what I just drew before. Here's 1, here's 2, okay, and then this part here, this part here, this part here, and we get up to 3. And then here's what we do differently. If we have reheat and we have 2 turbines instead of 1, it might look something like this. You might drop, reheat, and then drop again, like that. Okay, and it's not exactly because this has to line up better than I have it. But you get the idea. You would have here the high pressure turbine, and then secondary, you'd have the low pressure turbine. And notice, by adding the reheat, I've essentially increased the area under the curve here by adding this extra section here. Because instead of just straight dropping it off, now I've got a reheat, I've kind of moved more area to the right, and I have more total area inside this, right? And so that's going to give me more efficiency, more work, okay, by doing this reheat. And yes, 3, 4, you can keep doing it, but at some point it's just not worth it. But that's a visualization there. I wanted you to visualize. There's you'll have multiple turbines that help add area in the TS. Let me label this. This is a TS again. Temperature, entropy.
This is the graph associated with number 1.
It's the same graph. Yeah, same graph, except now I've added this extra turbine. That's all. Okay? Yeah. Yeah. Yeah.
So when a company is building a nuclear power plant,
Yeah.
do they look for spots that don't have a bunch of water on it also mean the fire lane is naturally cold to get that temperature lowered?
Well, you pretty much have to build, especially a nuclear power plant, but most all power plants are built near some kind of body of water because you need the cooling. It doesn't have to absolutely happen, but it's going to limit some of your ability to run a big power. If you have a big power plant, you're going to need to have somewhere to cool, and water works a lot better than air. So yeah, you pretty much, if you look at every nuclear power plant in this country and around the world, it's pretty much always built near water. So yeah, because you need to have cooling water somewhere. You need to be able to reject heat to the environment. So yeah.
Same equipment for two reactors.
Yep.
One's, say, Southern California.
Yep.
While the other one's in Siberia.
Well.
Siberia would be more efficient just because that initial temperature as well was going in the pump.
No, not necessarily, because again, the air temperature is not very good at cooling things off like water is. And so what you learn in heat transfer, there's something called the heat transfer coefficient. Heat transfer coefficient of water is about 1,000 times what air is. We think of air as an insulator. We never think of water as an insulator. Okay, a water it transfers heat almost 1,000 times better than air. So it doesn't really matter what the temperature of the air is. It still does a pretty crappy job of transferring heat compared to water. So it's all about the water. And in Siberia, if you had ice, I don't think that'd be good either. So yeah, you need liquid water. So yeah. You'll learn about that. But it's an interesting concept to think about. Well, what about, you'd have natural cooling in the cold air, but it doesn't do a very good job. Air is not a good way of cooling things. I mean, in your car, it's fine. But even in your car, you still have a cooling system, right? I mean, if we just totally air-cooled it, that'd be difficult, okay? So we have a cooling system, even in your car. So, okay, so there's multiple turbines. Now, another thing we can do, and this is all modern power plants do this as well, we superheat, meaning we actually have pressures inside the turbine, the maximum pressures greater than 22 megapascals. All modern power plants pretty much do that these days. Okay? Now let me draw that for you in another color here. I'll have to use red. What that essentially is doing is something like this. It's hard to draw what it looks like exactly once you get it above the dome, but let's just pretend it looks something like that. It would look something like that. Basically, what I'm saying is that it's above the dome. Like we bring the pressure so high, it's above the critical pressure. It's above 22 megapascals. Well, can you see how clearly my red box is bigger than the blue region? Yeah, because I brought the pressures up real high. So that's another thing we do. We try to get the pressures up as high as possible. But again, we're limited by materials. We're limited by the cost of building these things because we got to have good materials and a lot of it to hold pressures. 22 megapascals, that's 220 times atmospheric pressure. That's a lot of pressure, you know. So that's another thing we do. We try to increase the boiler pressure. And the last thing we do, and again, all modern power plants do this, is something called regeneration. Okay? Regen is what we call it for short. Regen, think of regen as recycling. Okay? That's kind of what, in fact, recycling is kind of what we do here, right? We say, hey, we got a boiler, why don't we use it a lot, right? Same thing kind of is true with regen. We have extra heat, why don't we use it? Okay? So here's what we do. Regen is not so much on the top, regen's on the bottom. When you have a turbine, okay, so here's your turbine, and you got stuff coming out of it, and you take it to your condenser. Okay, we're happy. And then before we take it to our pump, before we take it to the pump, we actually pull a little bit of steam, a little bit of hot stuff out of the turbine, and we bring it together with our condenser, and we use something that we call a feed water heater, FWH. Feed water heater. Okay? These feed water heaters might be open, which means that they mix together, which means the mass flow out of the turbine might mix with the mass flow out of the condenser. They might have a direct contact mixing, or it might be closed where there's no mixing. And that means that they just exchange heat. That's just a heat, what we call a heat exchanger. Okay? Regardless of whether it's open or closed, that's what we take, what we have out of that, out of the feed water heater, then we'll pump it. Okay? Okay? So that's regen. Regen basically says, you know what? That boiler has to do a lot of work. That boiler has to take liquid water and get it all the way to superheated steam, right? You know what we'll do? Let's heat up that water a little bit. Let's heat up that water on the rebound, on the recycle, okay, in the feedback loop. Okay, let's heat up that water, and it will give us less work for the boiler. The boiler will do less work because we're going to heat that water up a little bit before it comes back. It's called regen. It actually does help a little bit, and it's part of the process of a modern power plant.
Couldn't you just have instead of taking heat from the turbine and putting it into the feed water heater, couldn't you just forego the feed water heater and just make sure that the stuff coming out of the condenser is barely saturated liquid?
Barely well, we do, the stuff out of the condenser is saturated liquid. Yeah, I mean, that is. I mean, it condenses, so it's pretty much saturated liquid. But because it's at a pretty low pressure, usually, you'll see on Thursday an example, I think they'll make it clear. Usually we pump it up a little bit, we heat it up a little bit, and then we kind of combine it, and it does end up saving us a little bit of energy. So
It's kind of weird.
it is. It's like recycling. Yeah, it's like recycling. But yeah, you actually pull off a little bit, and it's more useful that way.
So with an open feed water heater,
Mm-hmm.
that's going to pump in liquid vapor mix.
No, we'll combine them so it's no longer a liquid vapor mix. If you bring in liquid and you bring in vapor, you have to obviously do the calculations, but we would never want that to go in the. Never want to have any vapor into the. Yeah, no. We don't want that.